We all know that feeling, don't we? You see that perfect apple, looks amazing,
Mm-hmm.
and then you bite into it. Ooh, mealy. Or a pear that's basically a rock.
Yeah, judging fruit by its cover, it rarely works out perfectly. It leads to a lot of disappointment. And waste, actually.
Exactly, which is why this idea of, like, seeing inside the fruit without cutting it, that's really interesting. Non-destructive testing.
That's the key phrase. And that's what we're diving into today, how sound, how vibration can actually tell us about the internal quality.
Right. So today's deep dive is all about that, using sound and vibration to get past the surface.
We're aiming to make this clear. We'll look at acoustic resonance analysis, that's about listening to vibrations to find defects, checked texture,
Okay.
and also acoustic vibration technology, sort of a broader approach. And, how specific frequencies can even hint at things like sugar levels or firmness. Get ready for some real aha moments from the research.
Okay, acoustic resonance analysis. Sounds complex, but you mentioned it's not totally new, right? It has history in other areas.
That's right. It's been used for a while, actually. Think quality control for things like roofing tiles.
Roofing tiles.
Yeah, or checking brake discs in manufacturing. The basic idea is you tap something and how it rings, how it vibrates. That tells you if it's solid, if there are flaws inside.
So how did someone think, let's try this on an apple? Seems like a leap.
It does, but researchers, specifically at the Leibniz Institute in Germany, ATB, working with RTE Acoustic, they saw the connection.
Yeah.
They realized, consumers want better quality produce, but we're stuck judging by size, color, stuff that doesn't guarantee a good eating experience.
We've definitely all been tricked by a pretty piece of fruit. It's what's inside that counts. Right?
Exactly. We need ways to spot internal damage, maybe from storage or handling. And really what makes fruit great, texture is huge.
Oh, absolutely. That crisp apple versus the soft, mealy one. Completely different experience.
Night and day. So finding a way to assess that without destroying the fruit is the goal.
So how do scientists usually test texture? I'm guessing it involves, damaging the fruit.
Typically, yes. They might measure the force needed to poke it with a probe, things like that.
Right.
But obviously you can't do that to every single apple on the packing line. You only test a sample.
Okay, so the acoustic method bypasses that. It's about listening.
Precisely. Acoustic resonance analysis. You give the fruit a little tap, some energy input, and it vibrates at its own natural frequencies. Research shows a link, a strong one, between the first main frequency and the elastic properties of the tissue.
So it's firmness, ripeness.
Exactly. It gives you clues about those things.
Is it like tapping a wine glass?
Yeah.
You hear the pitch?
That's a great way to think about it. Yeah, same principle. So RTE Acoustic adapted their industrial methods for apples.
Oh.
They built an automated system. A little mechanical clapper taps the apple gently.
Gently, okay. Important.
Very. And then sensors, some touching, some non-contact, pick up the vibrations.
And then what? Just measure the main pitch.
It's a bit more sophisticated. The vibration signals are converted to data. Software analyzes it, looking for specific features in that vibration signal.
Okay.
They use software, SR20AT is one example, to classify the fruit based on these features, and crucially, they check their work.
How?
They did destructive tests and even taste tests alongside the acoustic ones, just to make sure the machine's judgment of, say, mealiness matched up with reality.
Comparing the machine's opinion with human taste buds? That's smart. Essential, really.
Absolutely vital. And they had to tweak the sensors too, make them work on round surfaces in different packing house conditions without bruising the fruit.
Okay, so did it work? Can you actually hear a mealy apple?
The results are pretty clear. One study showed power spectra, basically a graph of the vibration frequencies.
Right.
For a fresh apple, the main pick was around 900 hertz. But after 4 weeks in storage, when it got mealy, that peak dropped.
To where?
Down to about 700 hertz.
That's quite a shift. So lower frequency means mealier, like it lost its tension.
That seems to be the case. And another type of graph, a spectrogram, shows this difference visually over time too. Fresh versus mealy apples have distinctly different vibration patterns.
Oh.
It strongly suggests this method can pick up on those physiological changes in the apple tissue.
So it's not just one note, it's the whole, vibrational signature.
Exactly. It looks at the whole vibration behavior, compares it to patterns it's learned, it analyzes the frequencies, how loud they are, how they change. It's a volume-oriented look.
Okay, that makes sense. Now, you also mentioned acoustic vibration technology. Is that different?
Slightly different approach, yeah. Resonance analysis often uses that specific tap. Vibration technology might use other ways to get the fruit vibrating, maybe shaking it gently or even just analyzing vibrations as it moves.
Ah, okay. Still about vibration, just maybe induced differently.
Right, and it's also a hot area of research. The core idea is similar. As fruit ripens, the cells inside change.
Microscopically?
Mm-hmm. And those changes affect how it vibrates. So analyzing those vibrations can tell us about firmness, other qualities. Acoustic theory backs this up.
How do they measure these vibrations then? Still sensors?
Yep. You need something to excite the fruit, a tap, shaking, maybe just movement, then sensors to detect the vibrations. Could be contact sensors or non-contact, like lasers.
Lasers sound very high-tech. And non-contact is good for speed, right? No bruising.
Definitely. Non-contact is great for high-speed sorting lines, but the research notes that where you excite it and where you measure and even how the fruit is sitting, that all matters.
Details are important.
Always. And you need good data analysis, good software to pull out the useful information and build reliable predictive models.
So we're building these sonic fingerprints. I was really interested in measuring specific things like sweetness. Can it really do that?
That's where it gets really versatile. Some research used special antennas, not sound waves this time, but electromagnetic waves to measure the Brix level, the sugar content in Malaysian oranges. They looked at how the waves at certain resonance frequencies reflected off the fruit, and they found a strong link between the reflection at one frequency, about 2.6 gigahertz, and the sugar level.
It's electromagnetic waves telling you how sweet an orange is. That's unexpected.
Isn't it? And back to mechanical resonance, they've used it for peach texture. They calculate something called a stiffness coefficient. It uses the resonant frequency and the mass. There's also this parameter S, calculated using frequency squared times mass to the 2/3 power. Sounds complex, but it relates to texture.
So generally, higher frequency, more mass, firmer fruit. Is that the gist?
That's the general trend, yeah.
Yeah.
Seen in apples, melons, pears. They even developed something called the elastic index, EI.
EI.
Yeah, based on the second lowest resonant frequency and mass. It correlates really well with kiwi fruit firmness.
Yeah.
And for melons, it was sometimes even better at predicting maturity than measuring sugars directly.
Wow, better than sugar measurement. That's a big deal for knowing ripeness.
It seems very promising. And get this, the EI might even predict how many days a melon has left until it's perfectly ripe.
Seriously, predicting the future ripeness.
Potentially. And for pears, a really low second frequency could indicate core rot inside.
Finding rot without cutting it open. That could save growers a fortune.
Huge potential for reducing waste. Now, of course, with all of this, you have to ask, how reliable are these sensors? Are the measurements consistent?
Good point. You need trust in the tech if you're going to rely on it.
Exactly. So studies have looked at the repeatability and reproducibility, the R&R of sensors like the AWITA AFS.
What does that involve?
Well, this sensor uses a tiny electromagnetic hammer, a microphone, and a scale for mass. Researchers tested it on 10 different apple varieties, measured mass, and lots of sound characteristics, peaks, valleys in the frequency spectrum.
Okay, testing its consistency. What'd they find?
The R&R results were good. The sensor was capable, meaning the measurement system itself wasn't adding too much variation for mass and the key frequencies, within acceptable limits.
So the basic measurements are solid.
Mostly, yeah. One of the amplitude measures was a little more variable, but generally capable. But here's something else really cool they found.
Go on.
Each apple variety had its own unique sound signature.
Like a fingerprint.
Kind of. A distinct pattern in the frequencies and amplitudes. Using statistical analysis on 18 of these sound features, they could classify the variety with almost 100% accuracy on the data they trained it on.
99.75%.
That's amazing. What about apples it hadn't heard before?
Still really good.
Using cross-validation, accuracy was over 85% and nearly 90% if they focused on the best 13 features.
Incredible. So you could just listen to an apple and know if it's a Gala or a Fuji.
That's the potential, yeah. They even figured out which specific sound features were best for telling varieties apart, like the loudness of the third peak was highly discriminative. Opens doors for sorting by variety automatically.
So let's sum this up. It really feels like these acoustic methods are giving us, like, X-ray vision for fruit quality.
That's a good way to put it. It's a powerful, non-destructive way to see inside, reveal things the eye can't catch.
And it's way beyond just, is it firm or not?
Oh, yeah. Identifying variety, ripeness stage, finding hidden rot, maybe even predicting shelf life. The potential is huge.
Okay, final thought then. Picture this. A future where every piece of produce gets a quick sound check for its real quality. Think about the reduction in waste, the improvement in, just enjoying our food.
Yeah.
Makes you wonder, what else could we listen to? What other surprising uses could come from this?
That's a fantastic question to leave things on. It really does stretch the imagination about where this technology could go, maybe checking other foods, monitoring quality during transport. Definitely exciting possibilities, and worth keeping an eye on the research in this whole non-destructive assessment field.